Hi, I'm Adam Paisley with Schnabel Engineering, and today we're going to talk about geotechnical grouting. Hi, I'm Adam Paisley with Schnabel Engineering. Thanks for joining me today. We're going to talk about geotechnical grouting. So let's jump right in. And let's ask the obvious question, what is geotechnical grouting? Well, grouting is a process during which subsurface materials, conditions, are modified by injecting a pumpable grout to achieve the desired performance. To better explain what grouting is, we're going to explore the pertinent components of this statement. Starting with a geotechnical grout. What is it? A geotechnical grout is a pumpable material which is used to modify subsurface conditions. Typically, there are two types of geotechnical grouts: non-particulate grouts and particulate grouts. The difference being non-particulate grouts are purely fluid grouts with no particles in them. Particulate grouts obviously have particles in them. Non-particulate grouts consist of one or more components which are in a liquid state at the time of pumping. Whereas particulate grouts consist of one or more dry particulate components which are mixed with a liquid component prior to pumping. The dry components are added to the grout mix in a defined sequence and mixed for a selected time to achieve desired grout properties. Chemical grouts, or solution grouts as they are more commonly called these days, consist of multiple components which cause a chemical reaction when they are mixed. Solution grouts comprise the majority of non-particulate grouts. Acrylamide and acrylate grouts form a gel like the example shown here. These grouts flow similarly to water. They have a similar viscosity to water, such that they can permeate small voids like soil pores and fine rock fractures. Additional components can be added to these chemical grouts to control the reaction rate to allow for a desired penetration prior to the grout turning into a gel and no longer being able to flow. Another solution grout example is a urethane grout that consists of multiple components which cause a chemical reaction when mixed, similarly to the acrylates and the acrylamides. But urethane grouts are viscous, fast-curing resin grouts and may appear similar to spray foam insulation that many people have seen. These grouts are typically much more viscous than water, such that access to smaller voids is very limited. However, these resin grouts are not reactive with water. They're hydrophilic. They can have very high strengths and are very effective in stopping larger leaks and larger seepage paths. Another form of non-particulate grout is called a hot bitumen grout. It's a very specific type of bituminous material which exists in a liquid state at high temperatures and is used to fill large subsurface voids. Imagine heating a tar-like liquid to 300 degrees Fahrenheit and pumping it into the ground as fast as possible to control a large groundwater flow. The grout quickly increases in viscosity when it cools and eventually solidifies at in-ground temperatures, typically around 55 to 60 degrees. This method is very specialized and is performed by a limited number of contractors and is often used as a last resort due to the required safety precautions and thermal infrastructure, and additionally to the higher cost. Particulate grouts typically consist of cement and water and often include additives and admixtures. There are particulate grouts which do not contain cement, but cement is typically used so that the grout hardens once the injection process is complete. There are multiple types of cementitious grouts, each with varying cement content, which is selected based on project goal and grouting process, as we will see shortly. Additives may include bentonite to aid in maintaining particle suspension, pozzolans like fly ash, silica fume, ground blast furnace slag, which each can delay cement hydration and promote long-term durability. And also even soil can be added as an additive for controlling consistency and performance during pumping. Admixtures tend to be chemical, such as superplasticizers, set retarders, accelerators, for helping control set time and for modifying viscosity. Cementitious grouts are often classified as low mobility grouts, or LMG, or high mobility grouts, often referred to as HMG, based on viscosity, purpose, and performance. You can see the difference clearly in the two images shown here, where the high mobility grout is clearly flowing like a fluid, whereas the low mobility grout looks more like a mortar. High mobility grouts have higher water cement ratios. They tend to include fluidifying admixtures and are often used to penetrate soil pores, rock fractures, and other finer void spaces. Lower mobility grouts have lower water cement ratios. They tend to have a consistency closer to a mortar, like we said a moment ago, and are typically used to backfill larger spaces and to displace subsurface materials. So having reviewed the grouts that are used in geotechnical grouting, we will now look at the processes in which the grouts are used. The grouting process is the method that is used to deliver the grout and to modify subsurface conditions. The process is considered to be either disruptive or non-disruptive based on the final modified condition. Disruptive grouting processes modify the structure of a formation through displacement or erosion, whereas non-disruptive processes fill void spaces but otherwise do not alter the formation structure. One example of a non-disruptive process is cavity filling, which involves the use of low mobility grouts, again the thick mortar-like grouts, to fill larger open subsurface spaces. The open void space is backfilled, but the structure of the surrounding formation is not altered. This process is often applied to abandoned mines and utility spaces, but can also be applied to open defects which form beneath man-made structures. Another form of non-disruptive grouting process is soil permeation grouting, which involves the use of thin grouts to fill void spaces between soil particles. The pore spaces between the soil particles are filled with grout, but the structure of the soil formation is not altered. This process is often applied to control groundwater or reduce compressibility of the soil formation by strengthening that soil formation. As the size of the pore spaces tends to be pretty small, this process tends to be performed using solution grouts or cementitious grouts with very fine cement particles called microfine cement or ultrafine cement. Another non-disruptive process is called rock grouting, which involves the use of thin grouts to fill discontinuities in a rock formation. Fractures, joints, bedding planes, and other discontinuities are filled with grout, but the structure of the rock formation is unaltered. This process is often applied to groundwater for groundwater control or to reduce compressibility of the rock formation by solidifying the rock formation. This process tends to be performed using high mobility cementitious grouts, and a number of and variety of admixtures and additives can vary pretty widely depending on the project. On to disruptive processes, the first being jet grouting, a rather violent process that is performed in soil formations by injecting thin cementitious grouts at very high pressures to erode the soil and to create soil creep columns. So imagine 300 bar, it's a few thousand psi of pressure being used to inject a high mobility grout into soil formation. The structure of the soil formation is altered by the erosion that is caused by the high pressure jetting, and a new soil creep structure is formed. Soil creep being similar to concrete, whereas instead of aggregates and manufactured sand, you have soil particles filling in the spaces. This grouting process is often performed to control groundwater, increase soil strength, and or provide excavation support from the sides or the bottom of an excavation. Typically, the grout is a neat cement grout, meaning that it contains only water and cement, but air may also be injected with the grout to achieve the desired performance and address certain subsurface conditions. Admixtures may also be used depending on site conditions and the project goals. Another disruptive process is compaction grouting, which is performed in soil formations by injecting thick, low mobility cementitious grout to densify the soil. The soil formation is compressed during injection of the thick grout, meaning that it is altered. It should be noted that this type of low mobility grout is specifically designed for this application. Grouts and procedures used in other low mobility grouting applications should not be assumed to be appropriate for compaction grouting. Compaction grouting is a very special form of low mobility grouting, often confused with other forms of low mobility grouting. Compaction grout includes cement and additives such as soil, gravel, fly ash, other pozzolans, other bulk additives which contribute to a desirable additive or aggregate gradation. This grouting process can be performed to increase soil strength, reduce settlement potential of the modified formation, improve formation stability, and in some cases also reduce permeability. Another disruptive process is compensation grouting, a very specialized grouting process which is performed in soil formations by injecting thin grouts to compensate for settlement caused by underground construction. Yeah, imagine that you've got a tunnel that is being excavated beneath a downtown large city area where you've got multiple story buildings that would pretty easily be damaged if part or most of any one of the building footprints were to settle. Thin, typically cementitious grouts are injected into the soil above the underground construction, like tunneling, to limit the negative displacement or settlement of the overlying structures. The grout is used to intentionally fracture the soil to create force within the fractured lenses in the direction opposing the undesirable displacement. So in the case of if settlement is undesirable, which is the case in most cases, you would create a vertical force to resist the settlement and maintain the vertical location of the overlying structure. Instrumentation is used to measure displacements to inform grouters for selection of appropriate grout pressure and flow. Displacement grouting, as kind of a loaded term, it's performed by injecting grouts beneath structures or objects to cause a desirable displacement. In this case, we actually want to move the object above the soil mass. This grouting application can be performed with particulate or non-particulate grouts with a variety of properties. Depending on the site conditions and the grout properties, this process may cause disruption to the formation or may simply fill a void and then displace the overlying object. This process is commonly performed to lift slabs or structural foundations which have settled. The image shown here shows an example where a structural foundation is being lifted using a urethane grout. The grout could very similarly be a cementitious grout, high mobility or low mobility. Could be a variety of other solution grouts, whatever the site conditions call for. Desired performance enhancements, such as soil strengthening, have been mentioned for each of the grouting processes discussed so far. The next few slides will provide a few more performance examples. Grouting is commonly used to create a soil zone or curtain of reduced permeability to control groundwater. This example illustrates how grouting is used to control groundwater flow under dams and into excavations. Depending on site conditions, this performance enhancement may be achieved in soil or rock by implementing any of a number of disruptive or non-disruptive grouting processes using particulate or non-particulate grouts. The grouting method and material must be selected appropriately to accommodate project constraints and site conditions. Grouting can improve strength and stability of subsurface materials to support work in excavations and limit the potential for post-construction settlement. Non-disruptive methods like permeation grouting can achieve results like those shown in the photo for select site conditions. But disruptive processes like jet grouting, compaction grouting potentially, are often more appropriate for this application. I'm going to speak a bit here about verification of geotechnical grouting. Another way to describe quality control, quality assurance, the way that we maintain quality throughout a grouting program. Quality control and quality assurance is essential for any construction project, no matter the discipline. But this is especially true for geotechnical grouting, as the work is often being performed without the ability to see or sample the final product. Verification of quality must be incorporated into every stage of a grouting project, from planning during design to development of contract documents, and of course through the testing and monitoring during the construction work. Real-time monitoring is necessary for any grouting work. It is essential that both the designer and the contractor provide on-site monitoring for any grouting program. The designer will need to confirm design assumptions, and the contractor will need feedback on contractor requirements. Additionally, it is worth noting that conditions should be expected to vary across any project site, and that all staff will need to work together to observe the variations and to make adjustments accordingly. Manual monitoring and logging of data and observed conditions is necessary at a minimum, though efficiency is reduced. In that case, monitoring and logging is limited to only one hole at a time. Manually logged data has value and is better than no data. The resolution of the data is limited, and the value depends on the detail of the log. In this case, this log shows that at most once a minute, a reading can be taken to record the conditions during grouting. The monitoring and logging of grouting data is significantly enhanced by the introduction of computers and digital instruments. Efficiency is considerably improved and challenges can be identified sooner. Staff in this photo are monitoring and logging data from 4 holes simultaneously. The data is then sent to a database and plotted automatically on a digital profile shown up in the top left. Clearly, the use of computers adds significant value to monitoring efforts and also enhances real-time evaluation of the grouting data. Once the data is collected and reviewed, it must be plotted in a visual form, such as the profile example shown on this slide, as the work progresses. This practice effectively informs all project staff of progress and results. It promotes effective planning and improves the overall grouting program efficiency. Grouting work is performed in a sequence such that the effectiveness of work completed in one grout hole affects the results of work performed in the next grout hole, and so on. Since conditions are expected to vary, as we said previously, at least a bit across each project site, the comparison of grouting results will inform a grouter about changes in site response. In these ways, spatial data evaluation will indicate grouting program effectiveness, will inform decisions for making adjustments to the grouting program, and will offer progressing verification of quality throughout the program. Before signing off here, I'd like to note a few references that have been helpful to me throughout the years doing grouting work. Adam Clive Holsby and Ray Henn offered considerable contributions to the grouting industry, these 2 books being only a portion of those contributions. These references have been around for many years, but they contain information which is still relevant and useful. Holsby tends to focus on grouting from the surface, while Henn offers guidance on grouting for underground construction. These 2 more recent references offer a wide variety of guidance on modern grouting technologies and methods. The content in Weaver and Bruce, in the Weaver and Bruce reference, does focus on grouting processes for modifying dam foundations, but also offers insight into grouting technology in general. Based on the content in their 2017 Grouting Technology Manual, the Army Corps of Engineers clearly aimed to cover a wide variety of grouting materials and methods, as well as offer guidance for design and construction phase processes. Last but not least, these 2 references published by ASCE and provide very specialized value to the grouting industry. The reference on verification, unfortunately, has been out of production for some time, but it includes expanded instruction on controlling and assuring quality in geotechnical grouting. I'd like to note that the ASCE Geo-Institute Grouting Committee is currently working on an update to this document to account for the changes to the grouting industry since the original reference was published. The current expectation is that the new version will be released for purchase in sometime in the next 2 years. The Compaction Grouting Consensus Guide was also prepared by the ASCE Geo-Institute Grouting Committee. It includes a guidance on compaction grouting design and construction, which has been reviewed by multiple qualified grouting industry leaders. This is the second version, such that it's been considerably improved since the first version, and is an excellent reference for anybody who is interested in learning more about compaction grouting or developing a program, implementing one in the field.
And with that,
I would like to thank you for joining me for this discussion on geotechnical grouting, and I hope that many of you find an interest in geotechnical grouting or another form of geotechnical construction. Enjoy the rest of your summer. This is Adam Paisley signing off.